This video, we're going to work on a few application problems here. So I have my TI-84 out here because we're going to have some big numbers to work with. I also have an image here to help us with the third problem so you can see what the different words mean, what they're talking about when we get to that problem. So the first one is going to be a bridge that is semi-elliptical. I'm going to choose a coordinate system that's centered at 0, 0. And it tells us the span of the bridge is 94, so half of 94 is going to be 47. It means that I have a point over here that's 47, 0, and a point over here that's negative 47, 0. They tell us that when I'm 26 feet away from the center, so I'll do that over here, that I'm 8 feet high. And they want to know what this height of the bridge is here, which is going to be b in my formula, since that's going to be my my distance from my center to the additional point along the minor axis. So we have x squared over 47 squared plus y squared over b squared is going to be 1. And so then I'm going to stick in these numbers for this point. That means that I have 26 squared is 676 over 47 squared. It's going to be 2209 plus 64 over b squared equals, and I'm going to make the right hand side 47 squared over 47 squared. So when I do the subtraction, get 2209 minus 676 over 2209 is 1533 over 2209, which means that b is the square root of 64 times 2209 over 1533. And let's type that into our calculator. 64 times 2209 divided by 1533 is about 9.6 feet. For the height of my bridge. Let's go ahead and erase this. Now we have a bridge that's semi-elliptical, but it's taller than it is wide. You know that because it says that the height is the major axis. So this bridge is like this. The top of the arch is 30 feet above the ground. And we're centered at 0, 0 again. And they tell us that there's a point that is 28 feet away from center. That's 15 feet above the ground. So I'm going to set this one up as x squared over b squared plus y squared over 30 squared equals 1. And make my substitutions at 28 squared over b squared plus 15 squared over 30 squared is equal to 1. 15 squared over 30 squared is the same thing as 15 over 30 squared is 1/2. Squared is a quarter. So that's just much easier to do that than to get 225 and 900 and have to figure that out. So we have 28 squared over b squared plus 1/4 is equal to 1, which makes 28 squared over b squared equal to 3/4. And that makes b equal to the square root of 28 squared times 4 over 3, which is about 32.33. There's a bunch of stuff there. I want to know the entire span of the bridge, which is going to be 2 of these. So that's going to be about 64 feet. Now for the problem that I have the picture for, and I'll make the picture bigger so that you can see what I'm doing. Let's bring it over here. Okay, so we have a planet that is in orbit around the sun. The sun is one of the foci of the ellipse here. There's the center of the planet's orbit there. This shortest distance from the planet to the sun is called the perihelion, and this longest distance away from the sun is called the uh, aphelion or aphelion. Not sure how you say that, but it's Helios is sun, so probably aphelion. The mean of those two numbers, the shortest and longest, is the distance from the center to the end, is the value that we would call A in our equation. And the distance from the center to the sun, that's going to be C because the sun is one of our foci. So let's see if I can get this going here for you. We're going to let all of our distances here be in millions of miles. So where it says 375 million miles, I'm just going to use 375. So we have x squared over 375 squared plus y squared over something that we're trying to solve for is equal to 1. So now let's go ahead and try and solve for this b that goes in here. To do that, we're going to need to find c, because the difference between a squared and b squared is c squared. So we're going to say that if the perihelion is 372.2 and the mean distance is 375, I can find the difference between them. to give me a distance of 2.8, and that's going to be my distance from my center to my sun. This distance from the sun to uh, the end of the major axis, we said was 372.2. So clearly this image that I have here is not to scale, but together they make the distance of 375. So then I'm going to take that 2.8 and I'm going to say that 375 squared minus 2.8 squared has to be my b squared. So b is about, stick this in my calculator, the square root of 375 squared minus 2.8 squared. And we get roughly 374.99, and that gets squared in the formula. So what we see here is that this planet has nearly a circular orbit, because if A and B are equal, then we have a circle. It's very, very, very close to having a circular orbit. It's only slightly elliptical. All right, I don't need the picture anymore, so I'm going to clear the entire canvas. And let's go ahead and look at this last problem, which is another arch that's semi-elliptical. And it's 52 feet wide at its base, meaning that this is 26 so, and it has a height of 20. They want us to figure out how wide the arch is when we are at a height of 12 feet. So there's some negative x 12 and some positive x 12, and our answer is going to be 2 times x. It's going to be this x and this x together. So let's go ahead and solve for x here. X squared over 26 squared plus y squared over 20 squared is equal to 1. And we know that we're looking for y being 12. And then this is going to be simplified to 3/5 squared is going to be 9/25. And this is going to be 25 over 25. So x squared over 26 squared is equal to 16 over 25. X squared equals 16 times 26 squared over 25. Everything there is a perfect square, making my life nice and easy. 4 times 26 over 5 is going to be exactly 20.8. And then I need 2 of those to get the width. So that's going to give me 41.6, and we are in feet. This was on 9, and this is millions of miles. All right, that's it for our application problems. I will see you again for our next conic section, which is going to be the hyperbola.